Hello, everyone. In 1913, Bohr published an article on the Bohr model of the atom, what we now know of as the Bohr model of the atom. And basically, he was using some evidence that Rutherford had found in the Geiger-Martin experiment. He was also using some evidence that Einstein had found, as well as the Planck quantum hypothesis. And he made this argument that basically, if we quantized angular momentum, he could actually explain the hydrogen spectra, and he in fact did. So in this presentation, I'm going to actually show you a derivation of how that hydrogen spectra can be explained using the Bohr model of the atom. And then I'll go through and show you how his ultimate quantization of the angular momentum is exactly the same as what you expect if you sort of applied a certain principle to the Broglie hypothesis, which was that the electron had a wavelength equal to h over p, its momentum. So I'm going to do that and then solve maybe a couple simple problems and show you a couple different simple ways to solve a problem. So let's get started with the document cam. So Bohr had come up with the idea of energy equals h times frequency, and in fact specifically that energy could only be 1 times h times frequency, and 2 times h times frequency, and 3 times h times frequency, and so on and so forth. And Planck had done that to explain basically the intensity of light emitted by a hot object, a hot solid object. And he got this, famous curve that the Rayleigh genes and Wien's laws couldn't actually, or Wien's expression couldn't actually explain. So that was our first quantum hypothesis. And then Bohr tries to look for a way to get something roughly the size of the atom using the mass and the charge of the electron. And he couldn't really find any kind of formula, any way you could combine the mass of the electron and the charge of the electron to get something with units of length, much less units of length, that has a value approximately equal to the size of an actual atom. But he did find that when you added the actual constant h, which was this quantum of action, as he called it, and as I think Planck called it as well, when he found that, he could actually get a unit. And what he ended up doing was arguing that the angular momentum, which we use the symbol L for, which is really, it's r cross p is what we normally say. So it's actually L, the vector, is equal to r cross p. And in terms of p being perpendicular to the radius, if we assume that the actual orbits of the electrons around the atom, the nucleus of the atom, again coming up with Rutherford's hypothesis, then we just get these two are perpendicular. So you get the mass of the electron times the velocity of the electron times the radius of the orbit. That's actually the angular momentum. And what he said was that it's actually equal to some integer multiple of h over 2 pi. So that's actually the Bohr hypothesis that angular momentum is quantized. And since we have an n there, we're going to subscript that rn, that r with an n, to show that that is the radius for the nth orbital, if you will. Now, that's all well and good. That gives us a good expression. And in fact, from that, we can calculate that the velocity is actually, all you have to do to solve for velocity is you divide both sides by Rn and m sub e. So you end up getting n times h over 2 pi times m sub e times r sub n. So now we have an expression for the velocity. You might even wish to call this v sub n if you wanted to, and it would be the velocity of the electron in the nth orbit, whose radius happens to be Rn. Okay, so that would actually work. Now we have some constraints on this. In order for this to actually be acceptable, we have to have Newton's second law be valid. And Newton's second law says the summation of the forces is equal to mass times acceleration. In this case, what we're talking about is this giant, I say giant in mass, this massive nucleus at the core sitting essentially still. And that giant core has a attractive force on the individual electron because that core would be positively charged, and we're going to keep it in a circular orbit. So for that to be the case, we have to have the Coulomb force, which for any number of protons would give us a force equal to Z times E squared. Remember, the charge of the electron is E, and then the charge of the proton is also E, except the electron is negatively charged. And then if we had any number of protons Z, then the charge of the nucleus would be Z times E. So that's why I'm doing ZE times E, which is ZE squared. And then the rest of the Coulomb force law is 4 pi epsilon naught. And then, of course, that'd be over Rn squared. So that's the force of attraction between the nucleus and the electron. But in order for that to keep it into a circular orbit, we'd have to have that equal to the centripetal acceleration, which is the mass of the electron times the velocity of the electron squared over the radius of the orbit. So with that, we can immediately see that one of the Rn's is going to cancel out. And that actually gives us an option, the ability to actually solve for the Rn. So let me start by basically plugging in that velocity here from there. Okay, so I'm going to take this velocity and I'm going to plug it into here. And now that I've canceled out the Rn, or excuse me, one of the Rn's, that'll give me Z E squared over 4 pi epsilon naught Rn is equal to Me, that's the mass of the electron, times the velocity squared, which is going to be N squared H squared over 4 pi squared Me squared Rn squared. So that's the new expression we have. We can actually make some cancellations. So for instance, we see a 4 on this side. That's going to cancel out with this 4. We see one of the pi's on this side. That's going to cancel out with that exponent of 2 and leave it a 1. We can see this Me on top is going to cancel out with one of these exponents of 2 and make it a 1. And then finally, we can see that this exponent of 2 is going to cancel out with this Rn and just leave a Rn over there. So now I can say, well, ZE squared over epsilon naught is equal to N squared H squared over, I've got a pi left in the bottom, so I'm going to say pi times M sub E times R sub M. And in fact, that allows me to solve for Rn. And doing so, I get Rn is equal to, so Rn is going to come on this side. Everything else is going to come down on the bottom. I'll end up getting N squared H squared epsilon 0 over pi M sub E Z E squared, which we might want to write in a way that's sort of lets us know the dependence on N. So I could write H squared epsilon 0 over pi M sub E E squared. And then that value will be multiplied by N squared over Z. So this would actually give you a nice expression for the radius for a given N. And notice this quantity is what would happen when Z equals 1, or excuse me, when N equals 1. So we would call that R1. You can calculate that and you might be surprised at what value you actually get. Now that we have Rn, what we ultimately want to do is figure out why does hydrogen emit the individual colors that it does when it's excited. So you take a glass tube, you create a vacuum out of it, then you backfill it with basically pure hydrogen. and then you cap it off with glass and then metal electrodes going through it, and you apply huge voltage to it, and it actually excites the gas and makes it glow like a neon light, only it's a helium light. And then you take that light and you run it through a slit, and you run it through say a prism, and that actually spreads the light out into individual colors of light instead of a whole rainbow that we get when we do that to visible light. We actually end up getting only certain colors from the rainbow, and we want to understand those. So in order for us to understand those, what we think is going on is perhaps there's electrons going from one orbital to another. And if I can figure out what the energy is for each orbital, I can subtract those energies, set that equal to Planck's famous E equals H times F, or E equals HC over lambda. Either one of those, and that'll give me the frequency or the wavelength of a photon that I might expect to be emitted or absorbed, depending on whether the actual electrons falling down, in which case it's emitted, or the electrons going up, in which case it's being absorbed. And hopefully that will actually work out. So that's what we're trying to do here. So we're trying to figure out that, but I've got to, now that I know V and Rn, I've got to actually calculate the energy of the actual atom in that state. So we know that energy is actually equal to potential energy plus kinetic energy. And we're going to assume that the atom itself, the nucleus of the atom, is not really moving because it's so massive. Remember, basically on the order of 99.99% or 99.9% at least, because the nucleus is on the order of thousands of times heavier than the electrons. The vast majority of the mass is going to be in the nucleus, so it's going to essentially not move as a result of the mass of the little electrons doing whatever they're doing. So what we're going to do is calculate what this potential energy is of the individual electrons in the atom plus the kinetic energy of the electrons. Well, that's going to be equal to the negative E, which is the charge of the electron, times the voltage established by the actual nucleus of the atom. So that's going to be added to the kinetic energy. So 1/2 m sub E times V squared. Whoa. V squared. Now that should be the total energy. Now the whole reason Bohr made this hypothesis that the angular momentum is quantized, it's equal to n times h bar, or n times h over 2, and that's what h bar is. H bar is defined to be h over 2 pi, where h is equal to 6.626 times 10 to the negative 34th joules times seconds. The reason why he did this was because if we thought, as Rutherford had concluded, that in fact the nucleus is this really large positively charged thing, and that the electrons are orbiting around it, not unlike the planets orbit around our sun, then that would mean charged particles, specifically electrons, are accelerating. And Maxwell's equations taught us that charged particles accelerating basically radiate energy. So they're actually losing energy, which would suggest that the electron losing energy would slow down. And then, of course, since it slows down, this equation can't be in equilibrium anymore because the V is too small, and this is going to overwhelm it and suck the electron into the nucleus, and therefore the atoms would not be stable. So what Bohr was suggesting is that maybe the laws of physics are a little different than we think, in that maybe at the microscopic level, energy is not radiated away from a charged particle if it's in what he called a stationary state, and maybe stationary states are defined by angular momentum being equal to a multiple of h over 2 pi. So that's what we're actually arguing here. So now we can set up this voltage and use this velocity, plug all this stuff in, and we'll get that the energy, which is going to be subscripted in specifically because we're going to have all of this as functions of n. So the energy of the nth state, meaning the nth orbital, if you will be equal to negative E times, now we're going to have the potential set up by the actual nucleus, which is Z times E over, as you know from Coulomb's law, this is 4 pi epsilon naught R sub n. And then from that, we can now multiply those two to get the actual potential, and now I've got to add in the kinetic energy, which will be m sub e over 2 times the square of the velocity. Well, the square of the velocity is n squared h squared, again using this formula over here, over 4 pi squared m sub e squared r sub n squared, just like that. So now we've got basically everything, but you can see these terms aren't going to add because this has an rn squared in the bottom. This has just an rn. So in the end of this, we really need to go ahead and get rid of the rn. So I'm going to cancel out as much as I can right now, but I'm then going to replace this rn squared with this quantity squared, and then I'm going to replace this rn with this quantity. So let's mark out what we can. I don't really see anything that I can cancel out in this term, but I do see that I can cancel out that square with this top number. I can make this an 8, and that's pretty much it. So now I'm going to begin doing the basically the hard work. So it'll be a negative z e squared over 4 pi epsilon naught. Now rn in the bottom means I'm just going to flip this rn expression upside down. So I'm going to put it as is, but upside down. In other words, I don't square it or anything. So now I put pi m sub e z e squared over n squared h squared epsilon 0. Now I'm going to take this other expression, which is the kinetic energy part, and I'm going to say n squared h squared over 8 pi squared epsilon, no, I know epsilon 0 yet, but m sub e is there. And then I have all that's left is the rn squared. So I'm now going to take this sucker and square it and flip it over. So now I've got a pi squared m sub e squared z squared e to the 4th, all that divided by n to the 4th h to the 4th epsilon 0 squared. So now I can start making some cancellations as needed. Obviously, this 4 is going to cancel out with all of these n's and just leave a 2. Similarly, this 4 is going to cancel out with all of these h's and just leave a 2. This m e squared, this exponent of 2, is going to cancel out with this me completely. And this pi squared is going to cancel out with this pi squared completely. I don't really see, like I said, any cancellations here. Oh, actually I do. I see a pi that can cancel out with a pi, and that's about it. So now I'm going to go back and write this as negative m sub e. Did I cancel out that? No, there is an m sub e. Z squared e to the 4th over 4. Taking care of all that. Epsilon 0 squared from that guy and that guy, n squared h squared. So I think I've got everything there for epsilon 0, n squared h squared. Yes. Now I have plus over on this side. There's no n's or h's left on top. There's no pi squareds, but there is a m sub e. So I'll write the m sub e, the z squared, which is good because it looks just like that. The e to the 4th power, which is good. It also looks like that. Then I have a n squared, running out of space on the page. Now I have an n squared in the bottom, a h squared in the bottom, a 8 here, a epsilon 0 squared. So I'm going to write 8 epsilon 0 squared n squared h squared. And that looks like it takes care of basically everything. 8 n squared h squared epsilon 0 squared. Yes. Okay. So now I've got all that. I can in fact combine like terms by multiplying this by 2 over 2. That would make that a denominator of 8. So it would match this. And then I'd have 1 minus 2, which should be negative 1. So ultimately, I should get negative m sub e z squared e to the fourth over 8 epsilon 0 squared h squared n squared. And that's basically it. I might want to express this a little more succinctly, if you will. And when I do that, that's kind of nice because I can ultimately write this so that I see how E depends on N, and I'll get negative m sub E z squared e to the fourth over 8 epsilon 0 squared h squared times 1 over n squared. And that is actually equal to negative 13.61 EV. In other words, if I take the time to calculate all this and then convert it from joules to EV, I'll get negative 13.61 EV over n squared. And this is our E sub n. So that's the energy of the nth orbit. In other words, the n equal 1 orbit would be the orbit closest to the nucleus. The n equal 2 would be the second closest. The n equal 3 would be third closest, and so on and so forth. And in fact, that defines the Lyman, Balmer, and Paschen series. The Lyman series, for instance, is all the decays that fall from n equal anything to n equal 1. So the Lyman series implies n to n equal 1. And again, this is where they fall down, so that's the emission spectra. The Balmer series, which is where we get our visible spectrum ones, is n down to n equal 2. And the Paschen series, which is Paschen, is when you go from any particular n to n equal 3. And you can see how that energy would work. So one way you could actually calculate what the energy difference is from n equal 3 to n equal 2 is you put in n equal 3, get an energy, you put n equal 2, get an energy, subtract the 2, that gives you an energy. If you then set that equal to hc over lambda, you could find the wavelength and you would be done. Or you could set that equal to h over h times f, and then solve for the frequency, and again, you'd be done. So that's a really nice way you can immediately calculate what wavelength or frequency you would expect for a electron transitioning from n equal 3 to n equal 2, and that should be something you can experimentally determine. But if we take that a step further and realize that what's going on at the end of the day is E equals 0 up here at basically infinity, and then there's a bunch of little orbitals, so on and so forth. They get closer, closer, and closer. Well, they get closer and closer and closer as you go up, but they get further and further away as you go down like this. And then, of course, the nucleus is way down here. That's the actually energy. So all these energies are negatives, which is why the negative 13.6 is there. That's why it's negative. These transitions, which go from here, this is n equal 1, this is n equal 2, and this is n equal 3. All the transitions that go from here to here to here, those are all the Lyman series. All the ones that go from here to here, so on and so forth, those are the Balmer series. And then all the ones that go from here to here to here to here, those are the Paschen series. So that's actually the structure of what we're looking at. If we decide to consider what the changes in energy are, what we might want to do is say that the energy of a particular photon, let's say E sub gamma, meaning the symbol for a photon, is actually equal to E n2 minus E n1. And what I mean by that is this is the final n value. So n equals 1, for instance, for the Lyman series, or n equal 2 for the Balmer series. And this is whatever it started on. So you could do that, but if you actually wanted the physical thing that we measure, you want either the frequency or the wavelength. So if I want the wavelength, I have to say, well, let's realize that the energy is actually equal to hc over lambda, so that 1 over lambda is equal to En2 minus En1 over hc. Now that's the big trick. Now that is in fact what gives us the Rydberg formula, which is the formula, that was actually curve fit, if you will, by a strong mathematician by the name of Rydberg, who was teaching at a girls' school at the time. And that actually gave us the value, but he had no physical underpinnings for why that formula worked. And he had a Rydberg constant in there that just he fit. But now we're going to get something that actually gives us the Rydberg constant and gives it to us in terms of physical parameters. So all I have to do is take this energy and divide it by hc. So if I divide that energy by hc and evaluate it for two different ends, then I'll get this. I'll say negative z squared. I should have put the me first, but I didn't. So I'll say z squared e to the fourth m sub e over, now I'm going to write 8 epsilon 0 squared. Now instead of h squared, it's going to be h cubed, because I got to divide by h. And I'm also going to add a c in there, which I didn't have before. So that's going to be a c. And then all I have left for that is n squared. So now I'm going to put final minus initial would be 1 over n2 squared, which you can write like this if you want, minus 1 over n1 squared. And lo and behold, that's the Rydberg formula. And this is, in fact, the Rydberg constant in terms of values that we physically know: the charge of the electron, the mass of the electron, epsilon 0, which is the permittivity of free space, the Planck constant, 6.626 times 10 to the negative 34th joule seconds, and then the speed of light. So this actually gives us the famous Rydberg formula. That is what won Bohr the Nobel Prize. Now, if we go back and look at this weird thing where Bohr decided to say L is equal to mvr sub n, which is also equal to n times h over 2 pi, if we take that into account, that de Broglie, and again, I have no idea how his name should be pronounced. I apologize to French people in the world that just are just disgusted by that. It might be de Broglie, I don't know. But anyways, de Broglie came up with the idea that the wavelength of an electron is equal to h over p. So if I go ahead and say that p is equal to h over lambda and put it in here, then I can say h over lambda times Rn, notice this is the p here, right, is equal to n h over 2 pi. You see immediately that the h's cancel out, and lo and behold, you get that 2 pi times Rn is equal to n times lambda. So with that in mind, you can look and say, well, when n equals 1, then the orbit, which might be a circle, the average orbit would be like that, but in fact the orbit of the electron would have one wavelength in it. So this would be the first half of the wavelength, and this would be the second half of the wavelength. And then n equal 2 would give us another average or midline for the wave, if you will. And now I'm going to fit, in fact, two wavelengths. So I go from here to 1/4 of the way, and then I go from here to here, and then I go to here. And now I've got, in fact, two wavelengths fit on a second orbit. The third one around would be three wavelengths. So they're really like standing waves, just like when you pluck a string, you can get this orbit, which oscillates back and forth. That's the fundamental. You can also get this orbit, this orbit, this orbit, which would be, in this case, and in this case, it'd be. So in these cases, it's kind of different in that the wavelength or the length of the string is, in this case, L equals lambda over 2, L equals 2 lambda over 2, L equals 3 lambda over 2, L equals 4 lambda over 2. In our case, it's always just L, the 2 pi r is equal to lambda, 2 lambda, 3 lambda, so on and so forth. So that's the explanation of why the angular momentum did work, is maybe they're actually acting like standing waves. So now if you wanted to actually use this principle to actually calculate, for instance, the first Balmer series, so the first Balmer series would be from, or let's do it the simplest one. Let's do the smallest energy from the Balmer series. So the smallest Balmer energy, that would be n equal 3 to n equal 2. So all you really had to do would be take the energy at n equal 3 and the energy at n equal 2 and subtract the 2. So E sub 3 is equal to, that's 13.6 divided by 3 squared. So that's 13.6 divided by 9. So I'll say 13.6, and we'll divide it by 9. And I get negative 1.511 EV. And then I say E2, which would be negative 13.6 divided by 4. That gives me negative 3.40 EV. So if I take E3 minus E2, I get positive 1.888 EV. If I set that equal to HC over lambda, then I should be able to find lambda. So it happens to turn out that there's some really nice constants in this world that make things a lot easier. For instance, HC is equal to 1,240 EV times nanometers. So if I use that, then I can immediately say, oh, well, lambda will come over here. I'll divide 1,240 by 1.88, and that'll give me the number of nanometers. So I say 1,240. That's the HC. I'm going to divide that by 1.88. And that gives me 656 nanometers, 656.5 nanometers is the wavelength. So that's one way. Now, in principle, I could have just used this formula and put in n equal 2 and n equal 3, and that should give you the exact same formula. But I think this way is a lot more physical, and it's a lot simpler formula to use. So I think that should help you understand better how the Bohr model of the atom was able to explain the hydrogen spectra. And in fact, it derives the expressions for you so that you can see how, in fact, as the energy which is related to the n gets higher and higher, obviously this radius distance gets larger and larger by n squared, and how the energy actually depends on n squared in the bottom. And then ultimately it gives you the Rydberg formula again, which ultimately Bohr was able to win the Nobel Prize for. So I hope this helps, and we're going to call it a day. Have a good one.